Hi everyone, welcome back. I'm Debasattam and you're watching EE635 Applied Linear Algebra. This is lecture number 4, module 2. In module 1, we have seen one level of abstraction where we have seen that this AX equal to B, that is a system of linear equations. For that, this numbers, that is the entries in the matrix A, entries in the vector B, and the solution, they do not necessarily have to be all real numbers. Yeah, instead they could come from any field. What is a field? A field is a set that allows us to add the elements there and subtract the elements there and multiply the elements there and divide the elements there. Yeah, the abstraction of this structure of a field involved 11 points for an axiom set. Yeah, that is, those are called the axioms of a field. And with that, we have realized that this Ax equal to B thing can be done. I mean, equations like Ax equal to B, posing them, solving them. Yeah, we can do this row reduced, to pose them as Ax equal to B problem with numbers coming from the field is absolutely all right. And also together with the fact that whatever we have learned for solving, as you know, as methods of solving these equations using uh, elementary row operations to obtain the row reduced echelon form for these matrices. These methods are going to work exactly like they did for real numbers for these for the case when the numbers are coming from some abstract field also, right? This was, as I said, the first level of abstraction. In this module, we are going to look at the second level of abstraction. So once again, uh, let us recall the meaning of the word abstraction. Abstraction means pruning away anything that is unnecessary, keeping only the necessary properties, and with that, try and apply these things to a larger, a larger class of problems. Okay, so far what we have been seeing is only what should I say? Only the objects that we dealt with were of this kind only, columns of numbers. Indeed, a matrix A is an array of numbers, and then that multiplies to a column of numbers. That gives me another column of numbers, right? Some of them are known, some of them are unknown, and from there, from that information, we're going to find out the unknown. But in all these things, remember what we did was only these matrix vector multiplications. So these are just numbers written in an array. But does that mean that what we have learned for these linear equation stuff apply only to these columns of numbers or arrays of numbers only? The answer is no. They actually apply to a much larger class of systems, much larger class of situations, right? So, like for example, suppose we are faced with this particular problem. Okay, let me just share my screen. Okay. Yeah, here we are. So suppose we have this particular problem, namely, I have function w1, which is say e to the power t plus 2 times e to the power minus t. Okay, I have another function w2. So this is a function of time, of course. This is a function of time, of course. E to the power t plus e to the power 2t. Okay, and then I ask the question that wt, which is some other function, say this function comes out to be minus e to the power minus t plus 2 e to the power t plus e to the power 2t, right? So I can ask the question that is W a linear combination of W1 and W2, right? How do we solve this problem? This is one representative problem. Another representative problem would be replace these functions by, let's say, random variables. Suppose I have one random variable, I have another random variable, say x and y, and another random variable z. And I ask the question, is the random variable z a linear combination of the random variables x and y? Yeah, no one can stop me from asking this question, from posing this as a problem. And this is not just some cooked up problem, that I'm just doing it for the sake of this course. Many practical situations, many engineering problems lets us ask these questions about linear combinations, even when the objects are not columns of numbers. So for columns of numbers, that linear combination is something that we have seen, columns or rows of numbers. We've seen how you take linear combinations of rows. But what if these things are not of this type, not rows of numbers or columns of numbers? In that case, if a question is posed like this, how do we solve it? Yeah, this is where the second level of abstraction that I have been mentioning comes into play. Yeah, so what are the properties, what are the absolutely necessary properties about these columns of numbers that we should retain so as to make sense while talking about similar questions involving functions or random variables or various other objects, right? So these properties will lead us to the axioms, new set of axioms, right? And those axioms will define an object which will be called a vector space. And once that object is defined, we will see that all these ideas that apply, all these situations to which these ideas, this notion of vector space applies to all those situations, what we have learned so far about linear equations will become applicable. Right? So now our job is to get those axioms for the object called a vector space. Before we get those axioms, let us try and see what motivates those axioms. So once again, remember what we are looking for is the set of properties that would let us define these linear combination stuff, and so that we can answer, pose at least questions like, is something a linear combination of something? Okay. So let us try and investigate, let us try and look closely what is meant by this linear combination thing. So we get back to something that actually physically makes sense to us, namely the three-dimensional vector space, three-dimensional Euclidean space. So what is a three-dimensional Euclidean space? Well, it has three axes, often called x, y, and z, but for the purpose of this course, we'll call them x1, x2, x3. Now here we have seen various properties like, vectors, their orthogonalities, yeah? Sum of vectors. But are all those properties that is there for this? So this is denoted by R3. All those properties of R3, are they really important as far as asking questions of linear combinations is concerned? Well, not quite. Whatever is required is the following. So here, in order to talk about linear combination, what we mean is something like this. See, every point in this space is can be designated by an arrow, which can be associated with uh, three tuple of numbers. Namely, in this case, I call them xi1, xi2, xi3. I can have another point, so another arrowhead, another arrow, yeah? And that is another tuple, eta 1, eta 2, eta 3, another 3 tuple. So this vector I will call as xi and this vector as eta. What is meant by xi plus eta? We know from our high school studies that xi plus eta is nothing but xi. What you do is you translate this vector here. So this is also the vector eta, you just translated it, and then just add them using the triangle law. This also allows us to say that the sum of these two vectors is obtained by the so-called parallelogram law. So form the parallelogram, complete the parallelogram, and then this, one diagonal of that parallelogram happens to be the sum of these two vectors, right? Now, let us look at this in terms of these numbers, xi1, xi2, xi3, and eta1, eta2, eta3. Notice that this xi1, xi2, xi3 happens to be the following. Okay, this component along x1 axis, this length is xi1. The component along the y axis, sorry, x2 axis is xi2. This length is xi2, and the component along the x3 axis is xi3. Similarly for eta, eta has this is okay. So this length here is eta 1, this length here is eta 2, and this length out here is eta 3. Yeah, and we know from our experience that the vector xi plus eta is given by xi1, xi2, xi3. Their sum is sum with eta 1, eta 2, eta 3 results in nothing but xi1 plus eta 1, xi2 plus eta 2, and xi3 plus eta 3 component wise addition. Moreover, this vector xi and eta that I had, I could also do something like, instead of taking just xi, I could just multiply xi by a scalar and get something like alpha times xi, where alpha is just a real number, right? And then instead of just xi plus eta, I may also talk about alpha xi plus eta, right? And this combination is going to be alpha xi1 plus eta 1, alpha xi2 plus eta 2, alpha xi3 plus eta 3. So the moment I can define sum of two vectors like this and scaling of a vector by a scalar, yeah, by something from the real number set, I can extend that idea to talk about linear combination of vectors. Okay, I look at these two properties of vector sum and scalar multiplication and use that to generalize this idea of a vector space. So I break the shackle of just Euclidean three-dimensional space, yeah, and take these two properties and embrace these two properties to define an abstract vector space. And that is what we are going to do now. Okay, so on to the axiom of vector space. So vector space must have two objects. So a vector space must have the following properties. Number one, it contains, okay, um, it has a field associated to it, F. Yeah, the elements of F are called scalars. Okay. Number two, it has a set V whose objects are, or whose elements are called vectors. Right? V has an operation or a rule called vector addition that satisfies the following. So the vector addition will have to satisfy the following few properties. Number A, for all, should I write it like this? Okay. Has an operation called vector addition. Okay, let me write it this way. Yeah? That associates to each v comma w in v the vector v plus w, and it satisfies the following properties. Okay, so for every pair of elements v and w in the set V, in the set blackboard V, v plus w is another vector, another element from the set V. So V is closed under addition. Yeah, whatever way this addition might be defined. But this addition must satisfy the following properties. Number A, it has to be commutative. So for all VW in blackboard V, V plus W equals W plus V. So commutativity for all V, okay, for all U, V, W in V, U plus V plus W is equal to U plus V plus W. So associativity, C, there exists a unique element 0 in V such that for all V in V, 0 plus V equals V plus 0 equals, oops, equals just, equals V. So this is the additive identity in the vector space. Remember, this 0 is different from the field, huh? 0 in the field. So this is called the additive identity. I'm not writing this out. Number D is for all V in V, there exists, although it doesn't have to, we don't have to say that this is unique, it will follow unique, but let's not care about that. Let's say it's unique. Yeah, let's assume that it's unique. For all V, there exists a unique W in V such that V plus W equals W plus V equals 0 in V. This W will be called the additive inverse of V. Okay, this is one operation, the vector addition operation. Then comes the scalar multiplication operation. V has an operation called scalar multiplication that associates to each alpha in the field and V in the vector space an element alpha V in the vector space, and it satisfies the following. Right? So in words, this would mean that the vector space is closed under the operation of scalar multiplication. That is, you take a vector multiplied by a scalar, then that multiplication, no matter how it is defined, must also be a part of the vector space. Must also be an element of the vector space. Okay. What properties now must it satisfy? Number A, one that is there in the field times V must be equal to V for all V in the vector space. We define this. We don't say that this is natural, this statically follows. It's not like that, but to define it. Number B is a kind of associativity for all alpha, beta in the field. So for all alpha, beta scalars and V in V, we must have alpha, beta multiplied over the field, and that scalar multiplied with the vector V is the same as beta scalar multiplied with V, giving a vector, this scalar multiplied with alpha. So some sort of an associativity. C. So there are two operations. So just like before for fields, we have to define how the two operations, how they play out with each other. Yeah, with respect to each other, how do they behave? So for all alpha, beta in F and V in V, we have alpha plus beta over the field scalar multiplied with V is the same as alpha scalar multiplied with V plus over the vector space now beta scalar multiplied with V. So remember that this addition is happening over the field and this addition is happening over the vector space. So this is vector space addition, this is vector sum. But this distributivity property would be there. That is how scalar multiplication and addition in vector space as well as in the field, they distribute over each other. Property number D will be another distributivity property where we have one scalar but two vectors V and W in the vector space. We must have alpha V plus W vector sum, and the scalar multiplication is the same as alpha V plus alpha W. These are the four, these are the axioms that defines a vector space. So then the ideal way of writing a vector space would be V. I must also say that there is this field and there is this addition and multiplication. This quadruple defines a vector space. In Word, we say that V is a vector space. Remember, because we'll be using this again and again and again. Yeah, V is a vector space over the field F. Yeah, let's quickly see some examples so that we feel comfortable with what we have learned. First example, of course, the example that we are absolutely comfortable with, I'm sure. R2, R3, yeah, in general Rn. What is Rn? Rn is, in words, is the collection of all n tuples of numbers from R. So all n tuples of real numbers. That is a vector space. It will satisfy all the properties. In fact, it is R3 or R2 from where we have, which has given us the motivation, which has given us the, what should I say, the template on which we have built this idea of axiomatic vector space. Yeah, so all those properties will hold for R2, R3, in general for Rn. So a typical element in Rn looks like either the round bracket or the square bracket, whichever you feel comfortable with, x1, x2, dot, 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 up to xn. So this is a typical element in Rn. Of course, together with that, one might also talk about Rn row vectors, right? So a typical element here is going to look like x1, x2, dot, 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 up to xn. And notice that all the properties that you have listed out for vector spaces, they satisfy for row vectors also. In fact, there are many engineering fields where people don't talk about column vectors. They talk only about row vectors. For example, cryptography, coding theory. Coding theory, people will always talk about row vectors. I don't know why, but always. Row vectors come naturally to them. For us also, when we were talking about, equations, those normals of a plane, of a hyperplane, if you remember the geometric picture, they also were row vectors, right? So row column doesn't really make much of a difference. They are essentially the same thing. Okay, we'll see the meaning of row vectors also from the point of view of dual space later on. Yeah, but that's that. I mean, this also is a vector space. Yeah, now with just a little flight of imagination, you will be, I'm sure, um, able to see without much difficulty that if instead I had C to the n, that is n tuples of elements from C. So the set of n tuples of elements from complex number set, this also is a vector space. Is a vector space. Yeah, you may not be able to draw pictures here beyond n equal to 2. Yeah, but still it's a vector space. Rows also will form a vector space, right? So easy vector spaces. In fact, not just C. Why should we restrict ourselves to C? Take any field. Yeah, do this. It's going to be a vector space. I'm not going to explain the meaning of that. Do I? Do I have to? Let me do it anyway. This is the set of n tuples of elements from the field F. So in the proper notation, I have to write F to the n is the space. It's the vector space. The scalars are coming from F. the addition is the element wise addition, and scalar multiplication also is element wise multiplication. Zero element is the all zero vector. That's the additive identity. Additive inverse likewise is defined as the element wise negative. Yeah, and all the rest of the properties like associativity, commutativity, all of them will follow naturally. So this is another example of a vector space, right? Sometimes things can be, uh, you know, the same set. So a V, the same set can be a vector space over distinct fields. They in that case should be treated separately. We cannot commingle them or confuse them. I'll give you an example. Like C is a vector space over itself, is a vector space over itself, but C is also a vector space over R. The two structures are different. So set wise, it is the same collection of complex numbers, but when you view it as a vector space over C, it's a one-dimensional vector space. When you view it as a vector space over R, it's a vector space of dimension 2. We'll define dimension very soon. But yeah, so the same set can be a vector space over different fields, and then they have to be treated differently. Okay, but that's not all. You can have all sorts of other vector spaces. For example, if M cross N, which is the set of all M by N matrices with entries from F is a vector space over F with element-wise addition and scalar multiplication. Indeed, yeah, go ahead and check that all the properties of a vector space will be satisfied by this. So this is also a vector space. So when I say vector, there is no reason why you should think only it's an arrow, something that has magnitude and direction. Those things work only when you were in high school, not anymore. For us now, vector space, a vector means an element of a vector space. Yeah. And what is a vector space? A vector space is a set that satisfies the properties that I have mentioned here. I have listed here the four properties, with property number 3, property number 4 individually satisfying 4 properties. Yeah, 1, 2, 3 has 4 properties, and 4 has 4 properties. These are the axioms of the vector space. That's not all. Let us think of something more exotic. Yeah, we are having a flight, a huge flight of imagination. That's why, that's the power of abstraction. So, okay, so let us define something more complicated. So let me number these things here. This is example number 1. This is example number 2. This is example number 3. This is example number 4. This is example number 5. I'm going to define example number 6. Example number 6 is, say, let S be a non-empty set and F be a field, any field. Okay. Define V as the collection of all functions from S to F. So it's a collection of all functions from the set S to F. Then V becomes a vector space where addition, so V is a vector space over the field F where addition is defined as F, okay, for F comma G in V, that is both of them are functions. F plus G acting on S is by definition Fs, which is an element from the field, Gs also, which is an element of the field. The field as addition, we add these two numbers. That is how you define F plus G. That is how you define the addition in the vector space. To understand, to distinguish between these two sums, let me put a subscript V here and a subscript F here. So this is addition over the field, and this is addition over the vector space. And multiplication is defined as for F in V and alpha in F. Alpha F must also be a function. We want to define it. Its action on S is by definition Fs is an element in the field. Multiply this by alpha, which is also an element in the field. So this product here is product over the vector space. This is product over the field. Right? I hope you understand what is happening. Yeah, check that all the properties would be satisfied because those properties are natural properties in the field. Commutativity of the addition, associativity of the addition, additive inverse, additive identity. Well, let me just mention that in this case, we'll define additive identity. Additive identity in V is nothing but the zero function, that is 0 is from S to F is such that every element S is mapped to the 0 of the field, the additive identity of the field. This is additive identity for the vector space here. Indeed, you see, if F is the 0 function, then 0 plus GS will be defined as 0S plus GS, but 0S is defined to be 0, so it's GS. So therefore, F plus G acting on S is equal to G acting on S for all S. So therefore, F plus G must be by definition equal to G, right? So therefore, so 0 plus G is G, and that is the property of the additive identity in the vector space. And of course, additive inverse of F in V is defined as minus F, which is a map from S to F. What does it do? Every S it sends to minus of Fs. Yeah, you can check that this is the additive inverse. Right? This example actually is quite powerful because you see this example shows that both Fn and Fm cross n, these two vector spaces, are special cases of this. Indeed, Yeah, f to the n is when we take s to be equal to the set 0 1 dot 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 up to n. Verify that this is true. This is your immediate attention problem. Yeah, and if m cross n is when s is taken to be all pairs ij, where I is from m to 1 and j is from I is 1 to m and j is 1 to n. Right? Think about this. This requires some thinking, but that is a job for you. Okay. We'll look at even more exotic definitions. Yeah, we are on fire. We're not going to stop. Even more exotic definitions. What? Okay. So define the set okay, define the set of okay, define the set C0, okay, C0 as the collection of all functions from the closed interval 0 to 1 to real numbers such that if is continuous. Yeah, you are going to verify that this is a vector space. Verify that C0 is a vector space over R. Yeah, then if what should I use? Fx, let's say, is, or let's say f xi, that's a better notation. Sorry. F xi, this is the set of all polynomials in xi with coefficients from f. Yeah, this is a vector space over f with the natural meaning of addition and multiplication. Yeah, this also is something that you can verify. You can look at f n variable polynomials, xi1 up to xi(n). This is also another vector space. 10 LoRa polynomials, f xi inverse is a vector space. Yeah, all these are vector spaces. Right. Now, so that this is where we stop, but there's no reason why you should think that this is an exhaustive list. There could be all sorts of situations where you end up getting a vector space, yeah, which have not been listed here, right? But the moment those vector addition and scalar multiplication properties are satisfied, it's a vector space. What benefit do we get out of this abstract definition? You see, everything that we're going to learn from this point onwards, yeah, till till the next few lectures, everything that we are going to learn is going to apply to all these situations, and we won't have to each time specifically say that, no, look at this particular set, it's going to work out there, this particular set is going to work out there. No, whenever these vector space properties are going to be satisfied, things that we're going to discuss are going to hold, right? So the first such abstract property that we can fish out of this abstract definition of a vector space is that for every abstract vector space, the idea of a linear combination of vectors is going to work out, right? So linear combination now becomes well defined. So, so let V be a vector space over the field F, then a linear combination is given by summation alpha I vi I going from 1 to k, where alpha I are elements from the field and vi are elements from the vector space V. Because it's associative, I don't have to say in which order these are being summed up. Doesn't matter, associative, so the order doesn't matter, right? And commutative, so once again, in which, not just in the sequence, or if you shuffle them up, doesn't really matter. So linear combination gets well defined. Right. Now, from these definitions, one can also prove certain things which may appear to be trivial for us, but trivial as in the sense, they are they appear to be naturally true when we think of vectors only as columns of numbers. Yeah, but what is surprising is the fact that they don't have to be true for only columns of numbers. All these weird exotic vector spaces that we have defined, even for them, this will be these things will be true. For example, so some observations, some observations. Number one, 0 in the field times a vector in the vector space is equal to, because this is because of the first distributivity property, must be this, no? But this means distributivity implies this is 0v plus 0v. Okay. So then if from both sides I subtract 0v minus 0v, because vector space allows subtraction of vectors, this is the additive inverse of 0v. This is 0v plus 0v minus 0v. So this will cancel out, this will cancel out. What will be left with is 0v. This is a vector plus its additive inverse, so it must be 0. So this 0v must be the 0 vector. So 0 times v is equal to 0 in the vector space. Yeah, so this is the first observation. This is true everywhere. And for columns of numbers, this is trivial, but for general case also this follows, and you have to prove it like this. Similarly, you can prove that if I have any scalar alpha times the 0 vector, then this is equal to alpha by the second distributivity property. This is 0 plus 0. So this is in the vector space 0. So this is the vector space 0. This by the distributivity property is alpha times 0v plus alpha times 0v. And once again, I subtract. So this is 0v. I subtract minus, so alpha 0v minus alpha 0v must be equal to alpha 0v plus alpha 0v minus alpha 0v. This cancels out, this cancels out. So I'm left with the fact that 0v is equal to alpha times 0v. So any scalar times the 0 vector gives me the 0 vector. Okay. One more important thing is if alpha is not equal to 0. So if alpha is a non-zero scalar, so it's from the field, so it's a scalar, but it's not 0, so it's from the field minus 0. And V is any vector in the vector space such that alpha times V is equal to the 0 vector. Then this implies alpha inverse exists because alpha is non-zero, so and alpha is coming from field. Alpha V is also equal to alpha inverse into 0V, but we have already seen that such things always produce the 0 vector. This is going to be, this associativity tells me that this is identity, this is 1, and 1 times V, remember one of the axioms says that 1 times V is V, so this is V must be equal to 0 in V. See, so what we are saying is if alpha is non-zero scalar and V is any vector such that alpha V is equal to 0, then V must be necessarily 0. So only the 0 vector multiplied to a non-zero scalar gives me the 0 vector. So then in other words, we have this nice property that alpha in F and if for alpha in F and V in V, we have alpha V equal to 0, then either alpha is 0 or V is 0. So the product of two non-zero things, a non-zero vector and a non-zero scalar, can never give me the 0 vector, which is an interesting property because this is not something that is always true. You see, for various number systems, non-zero numbers can multiply and give us 0. Think of modulo n operations. So like for example, think of modulo 4 operations. In Z modulo 4, I have 0, 1, 2, 3. There 2 is a non-zero number, but 2 squared is 4, which is 0. So 2 times 2 is 4, which is 0. So two non-zero numbers can multiply and give me 0. Yeah, but not when you have defined, not for vector spaces. In a vector space, no matter what field we have, field vector space, two non-zero thing multiplying can never give me in the scalar multiplication business. If it gives the 0 vector, then one of them necessarily has to be 0, either the vector 0 or the scalar 0. Okay, so as an exercise, and remember that all these things I'm deriving only from the axioms. I'm not using properties of columns of numbers. I have never said that this 0 vector is the 0 column. No, for 0 column, I can say that, okay, alpha times x1, x2, x3, x2, xn is alpha x1, alpha x2, and so on. And alpha x1 is a real number. So if it is 0, then either alpha is 0 or x1 is 0. No, I'm not saying that. I'm just using the axioms. Yeah, all these things that I have derived here, all of them follow only from the axioms. That's it. Okay. As an immediate attention problem for you guys, why don't you prove that minus 1 times V is minus V? Prove it. Okay. Together with that, let me dictate some other immediate attention problems also. Yeah. So check for vector space whether this set where the addition is defined in a weird manner. The multiplication, addition is okay, but multiplication, scalar multiplication is defined in a weird manner. Whether this is a vector space or not. Once again, another weird definition of addition and multiplication. Check whether this is a vector space or not. Another weird definition of addition multiplication. Check whether this is a vector space or not. This is a homework problem now, which is kind of a little difficult, but think about it. I'm saying that the solution set of a homogeneous system of equations, I'm saying that prove that this also is a vector space. If the set of equations is inhomogeneous, that is, there is a non-zero right hand side, in that case, check whether this still is the solution set is whether it's still a vector space or not. Okay. Yeah, do these checks, and then then please check out module 3 of lecture number 4. Okay, till then, bye bye.